so capacitors and inductors and the first order solutions. So looking at a circuit with an actual capacitor in them. Did you guys go over this one? You did do this one then. Okay. So I heard yes and no.
I do it.
Okay, specifically this circuit, did you go over? Not this circuit. Maybe this circuit. A circuit with these values in it, or a different circuit? Okay, so that would have been different. Okay. All right, so summarizing the steps, if I was to see this circuit, what would possibly be the steps that I want to take to solve this circuit? Anybody willing to share how you would start this? Okay. Okay, so you want to look at it, so redraw the circuit. So I call it t equals 0 minus, so this is right before a switch has moved, is what this means. Before a switch moves. So what this means is if I have a switch like this, the arrow meaning going down means it closes. So this means closes at t equals 0. So at t equals 0 minus in this circuit, that would mean redraw the circuit with switch open. And in this circuit, you are going to solve for specific values in it so that you can use those for the next step. So what would I be wanting to solve for in this first step?
Voltage and current across the capacitor.
Okay. So it's going back to IC is equal to C dVc dt. So it means that the current in there cannot change instantaneously. So this is what cannot change instantaneously is the current because of the derivative. So voltage could change instantaneously there. I could put different voltage across the capacitor, but what won't change instantaneously is that current. So that's what you're actually, well, anyway. Okay, so just kind of keeping that in mind. Right, CDVCD, IL, DVT, okay. I just had a brain moment. So the voltage and the current why I'm pausing here is because the capacitance, I think I said that wrong. So your capacitance doesn't change instantaneously because you model it with a voltage source. So now I'm drawing a blank. Okay, I'll get back to that one. Okay, so then the second step would be to redraw it. Oh my goodness. And I call this 0 plus, and this is right after the switch changes. In this case, the switch closes at t equals 0. And then this is the stage so in this circuit is where you're getting your initial values. Okay, so this is where I get my initial values. So now I'm going to solve for whatever variable I want, and that's what's going to be the initial value. And I'm going to back up 1 second. Why am I redrawing these circuits? Why am I finding these values? For what reason? Hint. What is this equation for? It could be voltage across capacitor. X can be any variable in your circuit. So when you have a first order, meaning one derivative within your equation sets, if you remember from math, you get a general solution form for that. So in our case, it always ends up being this form. So it's an exponential form. So it's a plus b e to the minus t over tau. So those constants are based on your circuit, A and B, and tau is also going to be a value that is going to be dependent on your circuit. So this is a first order solution, meaning first order means I have one derivative in my equation set. So first order meaning one derivative in equation set. So that means that's why I'm trying to solve when I have just one d over d dt. So this will be always the form of that solution. And so in that, these variables for A and B are based on the circuit variable. So this, if this is voltage, then this would be the voltage at infinity and voltage at 0. So that's why I'm trying to find those values to plug them into this form. So you don't have to go through the whole, like here's my differential equation, and now I've gone through the whole solution by separating the variables of it. I can provide you with a video on that if you have interest in going through that separation of variable method to get the solution of this. But you don't actually have to know even how to solve it as long as you know this form and you know where those values for the constants come from. So this is a step that you can just kind of go like, I just need to find those values, plug them into the general solution form. So that's why we are going through the redrawing of the circuit. So one of them, which is the first one that we were talking about, is going to be this value here, so x of 0. So once I get that, that's where my initial value goes. And then I need to now redraw the circuit to find the other two variables, which is x at infinity, and in this case, if it's VC, it will be VC at infinity. So that would then be my next step, is redrawing circuit at t equals infinity. And so this will be your x at infinity value. So once I find that value, I can plug it in there. And then I just have one last value, which is tau. And so tau is determining how long it takes to either, in this case, a capacitor charges up or it discharges. And for an inductor, the current will have an exponential form, either increasing or decreasing. And so for either one of them, it's always this exponential form. So the nice thing about that is like, well, I know my exponential form to get to 67% of it is what tau means. So this means the time, so this is called your time constant. And how long so our initial change, we usually consider that as our 0 point. So how long it takes from once I have that 0 point change, I say that's 0 time. And then from there, how long does it take to either charge up to 67% or discharge to 67%? So that 67% comes from just more of a standard definition of like, oh, when do I say it's almost fully charged or fully discharged? We say at 67%, we consider that to be fully charged or fully discharged. And that's where that time constant comes from. So to 67% of final value. So if it's charging, it's going to be charging up to that 67% of that value. And if it's discharging, it takes it from the value it was to 0. So it's 67% from that one. If that makes sense. So going back to the solution here, let's see. Okay, so here's our graph. So this is what an end graph looks like for the voltage across the capacitor. And at 7.3, I didn't, should be 6.7%. So at the value is 6.7 volts from 10. Oh, that's because it's 9. That's why. I was like, why is this not? Okay. So 67% of 9 is 7.3 volts. So 9 times 0.67 will be 7.3 volts. So that's where the 7.3 volts comes. And I can look down here and I see in milliseconds, this is 0.1 milliseconds. So this is my tau. So if I'm given a graph, I can actually say this is tau. My end value is 9 volts, so it's 9 minus 9 e to the minus t. I can draw this really quick. So looking at this graph, I can write this mathematically because it will be this. Oh, is it not? Okay, it's not 0.1.
Oh, no, the tau, the 9 times 0.67 isn't equal to 7.3.
Okay, that's why. Thanks. Okay, what is it? Oh,
It is 6.L3.
oh, that's why it's not. Okay, thank you. Okay. Say it again, it was what? 6.03?
Yeah, 6.03.
Thank you. Okay, I was like, this graph doesn't look right. That's why. Okay, so that's going to be 0.06. 0.06. Okay, that makes more sense. Okay, so 0.06 here. Should probably be about right here. 06 seconds is going to be, this will be 6.03 volts. And this is your tau. And that matches. So I could write that to be, looking at this graph, I can mathematically write this as 9 minus 9e to the minus t over 0.06 milli. And that would be the expression that's there. So this graph is of that 9 minus 9 e to the minus t over tau, in this case, is 67% of that. Okay. Going back to this. Okay, so redrawing the circuit at the initial time. Okay, so for tau, if it's going to be 67% of that end time, then we want to do it as the final circuit. So you're going to look at the final circuit and use that to find tau. And how you're going to do that is redraw the circuit again. at t equals infinity and put a to b. So in this case, the element I'm talking about is like the capacitor. So you're going to take out the capacitor and put A on one side of the capacitor and B on the other side. And then you're going to take a Thevenin from A back to B, and that's going to be your RTH value that you're using. And so that gives you your RTH value. For tau for a capacitor is RTH times the C value. Tau for an inductor is L over RTH. So you're finding that RTH value to find tau, and that will be the final circuit. And again, why the final circuit? Why not at the initial circuit? Anyone answer that one? Think back about what tau means. And tau is dependent on the final value of the circuit. So as it either goes all the way down or it goes up. So you don't care, like the initial time, it's not going to help you determine the tau. So you need that final circuit. Okay, so wrap your heads around that one. Okay, so then once you have all these values, then you can plug them into the general form equation. So that general form equation is that final plus initial minus final times e to the minus t over tau. Okay. All right, a couple nuances here. So when I draw the circuit at t equals 0 minus, what do I do with the capacitor? So I need to change, this is the common theme, is you're always going to change an element that is complicated into something that you know. So in this case, we're moving that capacitor, which is a time-dependent element, into an element we know. So voltage source, current source, open or closed is the options that you're going to have here. So capacitor, if you memorize or have this handy, if I have let something sit for a really long time, that means that dVc dt is not going to change anymore, right? So what happens to IC? IC will equal 0, which looks like what? An open circuit. So that's how you remember, what am I going to model this as? So that makes it nice, because then I'm like, okay, when I've sat for a long time and I have no changes, the capacitor will be open. So you assume it's been sitting for a long time, and then a capacitor is open. For an inductor, your equation is VL is equal L DIL dt. So again, if it's sat there for a long time, what happens? Is there a change in current over time if it's sat there for a long time? And you have only DC applied to it. So DC voltage is applied to it, it's sat there for a long time, you'll have a fixed value of current in the circuit, but there will not be a change over time after it's sat there a long time. So it's only at the initial time that I either switch a switch or change the voltage to the circuit will I have a change. So with it sitting there for a long time, my di dt goes to 0. So VL goes to 0, which means what? Yep, a wire, I heard it. So an inductor equals a wire. So you can either memorize that a capacitor will always be open and an inductor will equal a wire, but if you forget, you can go back and look at these equations and be like, oh, if it sat there a long time, that differential is 0, which means VL is 0 or IC is 0. And that is helpful to remember. Okay, so then right at the switch, you're gonna have the capacitor is gonna act like, do this, do it in green. So a capacitor you're gonna model as a voltage source. And it will keep the value from t equals 0 minus, and then an inductor will be a current source with the value that you find at t equals 0 minus. So that stage you're gonna change the capacitor to a voltage source and the inductor to a current source. And then in the final stage, again, it sat there for a long time. And so again, you're going to have that the capacitor is open and the inductor is a wire. Put it over here. So for this stage. Okay, so even though you have a derivative in there, you're gonna do the same Ohm's law, except for now Ohm's law is gonna be like IC is equal to C dV dt. And so you're gonna have that differential value in there. And then when you solve the full like V in here, I could write this. So say I want to find VC, which would be the voltage between here, and if I put ground there, so I'm going to call this VC. So VC would be a divider, so it would be Vn times well, this is not going to be easy. Anyway, it will be a really ugly equation. Because you don't know, at this stage, you don't know this value yet. So VC will be a division between the resistor and the capacitor. And the resistor the impedance of the capacitor is not necessarily just 0.1 microfarad. So I'm going to skip this one. Okay, let's keep going on. Okay, so let's solve this. So solution, or to get to the solution, you're going to have to redraw this circuit multiple times. So I am just get another add page. Okay, so I want to copy this circuit, and we're going to multiply it by 3. Go back to this one. That's not even better. Okay. Okay, 2, and then 3. All right, so t equals 0 minus. What did we do with the capacitor? So you have to decide 2 elements. One is where the switch is, and one is what the capacitor is doing. So what do we do with the switch at t equals 0 minus? It was open, right? Okay, so I leave it open there. What did we do with the capacitor? And it's open too. Okay, so now I have an open circuit. So what is my VC value here? 0. So that makes it easy to go t equals 0 plus I now put this is going to be closed. And the capacitor I changed to a voltage source with it equal to 0. And that's going to be the same value for VC of 0. So VC of 0 will be 0. So this is my initial value of VC of 0. Now the final one, I have 2 steps. Move this over here. And one is to get the value of VC. So in the final stage, what is the switch doing? Is it open or closed? Closed, correct. And then this goes back to an open, and I'm solving for VC there. So what value will VC be here? Correct. And what is well, let me go back, not quite correct. What is VR? What's going on here?
0 VR.
Correct. 0 Y?
Current.
Correct. No current, no voltage across that. So if I'm ignoring that, then I have just the 9-volt supply, right? So VC in this case will just be the same as this one. And I always put A as my positive side. But again, if it's not labeled, you would want to label it for clarity of what is the polarity on that one. So this would be a plus 9 volts, would be VC at infinity. And then the other step for VC, or at infinity, is to find tau. So for tau, the switch is in the final position, which is closed. And here you remove this and put A on one side to B. And then what do you do with the voltage source when you're finding the Thevenin equivalent? Or equivalent resistance?
It's
Correct. So I'm going to just short this one. And what is the resistance that it sees between A and B if I short this, when I short this? It's just 600 ohms, correct. So now I can write my general form equation in this form of, and what was VC at infinity? Correct, 9 volts, so I have 9 plus, and it was 0, remember in the very beginning, 0 minus 9, e to the minus t, and tau, sorry I didn't write tau all the way out, tau is RTH times C, so this is 600 times 0.1 microfarad. So 60 micro. seconds. And this is all in voltage. So that is my expression for VC of t. All right, questions? Does that look doable? Okay. So, although there's like multiple steps, they're not hard steps. They just, you have to make sure to do each one in order to get to the final solution. If you skip one, then you're like, I don't know what to do for that value. All right, so that's the graph of it. If I wanted to now find IC of t, it's going to be C dV C dt, and then I actually just differentiate that equation I just found. So I can just take C times this whole thing. And when I differentiate that, what is the differentiation of that? I'm just going to write this in forms of tau because it's a little easier. So if I differentiate 9 minus 9e to the minus t over tau,
Is it 1 over tau times 9e? The
uh-huh.
negative t over tau?
Yeah, so remember e to the minus t over tau is just going to be, so it will be, sorry, the differentiation of this dt is equal to minus 1 over tau e to the minus t over tau. 9 goes to differentiation of 9 is 0 because it has no t in it. So it will just be minus 9 times 1 over tau. So this becomes IC of t equals 0.1 micro times 9, and that's minus 9 over minus 1 over tau. So let me go backwards. So minus 9 times minus 1 over tau in this case is 60 micro, e to the minus t over 60 micro. And now this will be in amps. And so the minus cancels out with the minus, so that value in the front becomes a 0.015 e to the minus t over tau. Yes?
I just didn't catch where the micro came from.
0.1 microfarad.
Where
Micro
is that?
of which one?
Where,
This.
where is that in the equation? Well, I just, because you took the derivative of v, I just don't see where it came from on that second.
So C is the capacitor value. So 0.1 micro I put in there. So it was just a substitution of that one. Is that the micro you were wondering about? Okay. Yeah. So 0.1 micro is where that one comes from the capacitor value itself. Okay. All right. Why don't you guys tackle this one? So same steps, except for now you have a inductor. So go ahead and work through solving for this one to get VL of t and IL of t. And in this case, I would suggest getting IL of t first and then using started writing it right. VL is equal to L dIL dt. So getting IL of t first in this case would be easier. So go ahead and you guys can work together, work alone. And Luca and I will come around and Looking like most of you have gotten it, so. Okay, so t equals 0 minus, you're gonna have an open, and then this becomes a wire. And so you find that with an open here, that I will be equal to 0. So IL of 0 minus is 0. And then in all these, you start to see a little bit of a theme that if you're trying to find the element related to like an inductor and IL, that's going to stay exactly the same for the 0 plus. But if you have a different element that you're trying to find, you would need to use the current source for an inductor and a voltage source for the capacitor if you're just solving for that one before you solve for the inductor current in this case. So this one will be closed, and then this acts as a current source with current value of 0. So IL of 0 plus is also 0. So that's my initial value. And then for infinity, I have this is closed, and this becomes a wire, so my I in this case. And how do I know if it's plus or minus? If I don't remember, I can go and do my loop really quick. So in this case, my loop would have a plus here and a minus here. So plus Vn minus I times R equals 0. So I see that, yeah, I is going to equal a plus Vn over R. And so this will be my final value. And then for this one, I put A on one side and B on the other, and then I short the voltage source, so my RTH for tau. So again, this is at final, and so to find tau is RTH is R, and tau is L over RTH. So my final equation for IL of t will be Vn over R plus 0 minus Vn over R. E to the minus t, and tau in this case is L value over R. And this will be in amps. And so this will be my final equation for IL of t. And then VL of t would be the differentiation of this. It will be I DIL dt, and so I will take L times the differentiation of this, which becomes Vn over R divided by 1 over L over R, so that becomes this, so then that becomes just Vn e to the minus t over L over R. So that Vn e to the minus t over L over R. So that would be my expression for VL of t. All right, questions? Okay, just write this for a second. next one. Guys ready for another one? Okay. All right, so this one, finding the expression IL of t and VL of t. So just a little bit harder circuit this time. So go ahead and work on this one. So fun to talk to you guys about learning experiences and blowing up some components. Okay, so finding an expression for this. So same steps, we're going to redraw the circuit each time. Right here. So in this case, at t equals 0 minus, we're gonna have the switch was open, I think, yeah, open, and then this becomes a wire. And finding the current here will be, would you guys find the current? Thank you, 0, correct. No current flow. So no current flow here. And then this also will be floating because this one is floating. So there's no pathway back from one side of the plus 15 all the way back to it again. So without a closed path, no current flows in there. And so at So right after the switch with no current flowing, it's going to stay the same for the current itself. So it becomes a current source. And this closes, and then this is a current source with 0. So IL of 0, which is your initial value, will still be 0. Any questions about that one? Okay. All right, at infinity, the switch will be closed, and this turns into a wire also. And so with this one, you have several options to solve for it. Can I give you guys a little technique I like to use here? So this is called node voltage method. What it does is it combines your current summation and your voltage loop all in one step, so you can look by inspection and write your equation. So my current here, if I label this Vx, my current in this branch is going to be Vx over 15. Because Vx is from ground, let me highlight this. From ground to here is Vx, and then from here back to ground is I times R3. And so my I is solving that is just Vx over 15. So with the current going in that direction that I labeled it, I start with the node as plus, and then I take off any other voltages in the circuit. So current in this branch, so I basically am doing my current summations out of each node. So here, here, and here. So for this current, it was Vx over 15. This current is going to be Vx over 60. And this current is going to be Vx minus 15 over 20. And then I can solve directly for Vx. And then I just divide this over here, and I can get my value for Vx. And then I can just plug it into my I current. The other way of solving this would be to find that voltage Vx by a voltage divider and combine the 60 and the 15 together. So I think that ended up being let's see, 15 times 12 over 20. So Vx in this case ended up being, I think 5.625. And so I is just Vx over 15 for 0.375. Is that what others, did you guys get that? That got a value? Yes, okay, good. Okay, so two ways to do that. Node voltage I find to be the easiest because I can just write that and then put that in my calculator, and usually that's easier to find when you have multiple branches like this. But again, you can do it by a voltage divider. You just have to identify that those two branches need to be in parallel. So tau now from this, so we have a closed, and then this goes back to, I'm going to leave that open and put A and B, and then this goes to a short because it's a voltage source. So short for the, and then A to B. So now what is my R equivalent, or RTH? What is in parallel here? So what elements are in parallel? Okay, so 1 and 2, so we have 20 in parallel with 60, and then it would be added to the 15. So 30 ohms. So tau is L, which is 3 milli over 30. Or 0.2 milliseconds. So my final answer will be IL of 0 was 0, and this was 0.375 plus 0 minus 0.375 e to minus t over 0.2 milliseconds. And then VL I can find from L DIL dt. So L times 0.375, so this was 3 milli, times 0.375 divided by 0.2 milli, e to the minus t over 0.2 milliseconds. I don't think I have the value. Yeah, I don't have the end value there, but whatever that value is, that will be your voltage. Okay, questions on this? Guys feeling a little more comfortable? Okay, so homework tonight to get more practice with that. I'm just gonna briefly, or quickly I guess, kind of go through one more step that you can do. So the Laplace domain, you can actually do this with Laplace instead, and you can get what's called a characteristic equation. And so how you do the Laplace is that your L element can be changed over into an impedance, and then you treat it just like a resistance and analyze the circuit like that. And so you can change this over to the impedance side, which would be L times S. And for a capacitor, it will be 1 over CS. And then you treat it just like a resistance and can solve the circuit. So this is useful when you have more than just one element. So we know the solution, that general form solution for one element in the circuit, but what happens if we have 5? We're going to get a 5th order differential equation, and I don't want to solve that one by hand. So instead, we change over to the Laplace domain, treat them like impedances, and then we can actually get a full equation with S in it. And then if we want to find a specific value for a specific frequency, we can find a value for a specific frequency, or we can actually get more understanding of the circuit over all frequency ranges with the S still in there. So S would then change over to J omega, where omega is our frequency range. So that's how we can move from just the single differential equation into a more complicated solution. All right, so that's all I really wanted to cover today. I think, yeah, I don't think we have full time to go over this one. So this one has a final answer if you want to try it on your own as extra practice. All right, see you guys. So next week is fall break, so I will see you the Tuesday after the break. Have a good break.